Hi, today we're going to look at section 28.4, basic trig functions. So we're going to start off with the derivatives that we've already learned in class from before. So we got the derivatives of the 6 basic trig functions: sine, cosine, tangent, secant, cosecant, cotangent. Now what we're going to do next is look at the integrals of these guys. So if we remember that derivatives and integrals are opposites of each other, then we can just flip these guys around and change the derivative to the integral. And we get these following 6 integral equations. So since the derivative of sine is cosine, the integral of cosine is sine. Since the derivative of cosine is negative sine, the integral of sine is negative cosine, and so forth. So we have these really nice 6 trig equations that are the integrals. So again, they're just the opposites of the derivatives that we've already learned. So we're going to try some examples using these 6 integral equations. So we start off with the integral of x secant squared x squared dx. And what we're going to do is we're going to let u equal x squared, since it's the inside of a function, right? It's secant squared of x squared, so u is x squared. And then that gives us du equals 2x dx. And then we're going to divide both sides by 2 to get the 1/2 du equals x dx. So then, using the substitution, we get that the integral of x secant squared x squared dx is equal to 1/2 the integral of secant squared u du, which, according to the equations from the last slide, is equal to 1/2 tangent u plus a favorite constant. And then we replace u back with what it was, which is x squared. So we get 1/2 tangent x squared plus c. And remember that the good thing about integration is that you can always double check it. Differentiate 1/2 tangent of x squared and make sure that you get x secant squared of x squared. Okay, so let's try another example. Here we have the integral of tangent of 4x divided by cosine of 4x dx. There are at least 2 different ways we can go about solving this one, so I'm going to show you both of them. So the first way to do it is to notice that 1 over cosine of 4x is equal to secant of 4x by definition. So that is going to change our integral to the integral of secant 4x tangent 4x dx. Now again, we have an inside function here, so we're going to let u equal 4x, which gives us du equals 4 dx. And then we're going to, again, divide by the 4 so that we get 1/4 the integral of secant u tan u du. So just a very short u substitution there. And then again, by that first side we had, the integral of secant tangent is secant. So we get 1/4 secant u plus c. And then replacing back in what u is, we get 1/4 secant 4x. Again, plus your favorite constant. So that's one way to do it, changing 1 over cosine 4x to secant of 4x. Another way to do it is to remember what tangent is. So tangent of 4x is equal to sine of 4x divided by cosine of 4x. So if we replace that for tangent, we get the integral of sine of 4x divided by cosine squared of 4x dx. And again, we have a function being raised to a power. So we let u equal cosine 4x. So again, that whole thing squared is a function, so we let u be the inside function, the cosine 4x. We differentiate it, and we get du equals negative 4 sine 4x dx. And again, we're going to divide by that negative 4 on both sides when we substitute it in. So we end up with negative 1/4 the integral of u to the negative 2 du. So remember, that would be 1 over u squared, which is u to the negative 2. Integrating this, we get 1/4 u to the negative 1 plus your favorite constant. And then we're going to plug back in what u is. And we're also going to remember that u to the negative 1 is 1 over u. and u is cosine, so we end up with 1 over cosine, which, again, by definition, is secant. So we have 1/4 secant 4x plus your favorite constant. So either way, you get the same answer, and you can think of it 2 different ways. So if we go back to that original list of 6 integrals, we don't have the integral of tangent x. We don't have the integral of secant x, or cosecant x, or cotangent x. So we're going to look at those next. Each of them would involve some form of u substitution, and to do secant and cosecant, it'd be even a little bit more confusing, so I'm just going to show you the results, and the book might explain it a little better if you want to go into depth as to the why. But for now, I'm just going to tell you what they are. So the integral of tan x dx is equal to negative ln of the absolute value of cosine x plus your favorite constant. The integral of cotangent x dx is equal to positive ln of the absolute value of sine x plus your favorite constant. The integral of secant x dx is the natural log of the absolute value of secant x plus tan x. And then cosecant x is similar. It's ln of the absolute value of cosecant x minus cotangent x. And we'll see in the next couple sections where the ln comes from, since we're doing these out of order. But again, just for now, believe me, you can read into the book if you want about the why. So we're going to do some examples involving those guys. So our first example is the integral of 4x tangent x squared dx. So again, we have a composition, a function of a function. So u is going to be that inside function, the x squared. So du is 2x dx. And instead of dividing by 2 to get rid of the 2, what we're going to do is we're going to multiply both sides by 2 so that we get the 4x that we have over here. So instead of dividing by 2 and then making 4 times 2, we're just going to multiply both sides by 2 and get the 4x right away. And then using substitution, we get that 4x tangent x squared dx becomes 2 tangent u du. And then according to our equations earlier, this is going to be negative 2 ln of the absolute value of cosine u plus c. And then we're going to replace back in what u is to get negative 2 ln of absolute value of cosine x squared. And again, don't forget, you can always double check these. We know how to take the derivative of ln's and cosines and x squareds. So it's a couple different chain rules needed, but you can go backwards. Take the derivative, make sure you get 4x tangent of x squared dx. So the next example is a definite integral. So it's the integral from pi over 6 to pi over 4 of 1 plus sine x all over cosine x dx. The easiest way to do this is to split up the fraction. So we're going to put it as 1 over cosine x plus sine x over cosine x. And then bring these back into what they're actually defined to be. So 1 over cosine is exactly secant, and sine over cosine is exactly tangent. So we're just going to use the definitions of the trig functions. And then each of these guys, secant and tangent, we know what their derivatives are. Again, back to that list of equations. So the derivative of the integral of secant is ln of secant plus tangent. And the integral of tangent is, again, negative ln of cosine. So we just take those from pi over 6 to pi over 4. You can plug that into your calculator, and you should get 0.5348. Okay, so it's a little messy if you're trying to do it out by hand or anything, but use your calculator, use parentheses correctly. You should be able to get 0.5348. Another example is the integral of sine of 3x times cosecant 3x plus secant 3x dx. So the first thing we're going to do is we're going to distribute the sine 3x. So we get the following. And then again, we're going to use the definitions of cosecant and secant to simplify this guy. So sine times cosecant is sine times 1 over sine, which is just 1. So this is just 1. And then we have sine times secant. Remember, secant is 1 over cosine, and sine times 1 over cosine is exactly tangent. So this whole nasty guy with all these trig functions just becomes the integral of 1 plus tangent 3x dx. And then we integrate. The integral of 1 is x. The integral of tangent is, again, negative ln. And then the fact that we have the 3x, we use u substitution. U equals the 3x. That's how we get the 1/3 in there. We end up dividing u equals 3x by the 3. So we get this lovely guy. And again, differentiate it, use a little bit of trig identities, and you can get back to the beginning. So here's our last example. The integral of cosine to the 4th x sine x dx. So what we have here is a function being raised to a power. So it's cosine of x raised to the 4th. So again, we're going to let u equal that function. So u equals cosine x. We differentiate it, and we get du equals negative sine x dx. And then we plug it back in, and we take out the negative. So we get the negative integral of u to the 4th du, which is just negative 1/5 u to the 5th plus c. And then we plug back in what u is, negative 1/5 cosine to the 5th x plus c. And again, differentiate it, double check, make sure you get cosine to the 4th x sine x. So I'm going to show you a couple of identities that we actually come across in the next section, but it might be helpful, hint hint, for the classwork and the homework. So this first equation you might recognize. It's sine squared plus cosine squared equals 0. It's the main trig identity that you learned if you ever took any type of trig class. The following two come directly from this equation. So if we take this equation and we divide every term by sine squared, we get the following. 1 plus cotangent squared x equals cosecant squared x. And then if we took the original equation and divided every term by cosine squared x, we would get the following. Tangent squared x plus 1 equals secant squared x. So you might want to look at this one for the classwork, and you might want to keep the 3 in mind looking at the homework. I think there's even a hint in the syllabus about that. So try it out, try out the classwork, try out the homework. Let me know how it goes. Email me if you have any questions. Right, bye.